Okay, this is a recording for Monday, March 11th, third hour pre-calculus. It's kind of the second part, I feel like, of 6.3, which we had started at one point last week. Just to go over our schedule briefly, we'll have notes for 6.3 today and tomorrow. If possible, I'll record them. Tomorrow, I will start with some homework check time / work time, just because we're missing so many people. Then Wednesday, we'll finish 6.3 if needed, and then work on 6.4, vectors in the dot product. And the homework check for 6.3 will be on Wednesday. There is no class on Thursday because it's a conference day, and we'll have hours 5, 6, 7, 4. And then Friday, we should have this class, and we'll have the homework check for 6.3, and then the notes for 6.4. And I'm just going to back up a moment and just look at this. Maybe I feel like I wrote here, but I feel like I didn't know. I'm going to go over this parallelogram law. Oh, I know why. I had put up the parallelogram law, but I hadn't gone over it because it's been a little while. When we add two vectors, it's the way that we do that is when we have these two vectors, u and v, and we want to add them together, just like addition in numerical values. If I add 3 and 4, or I add 4 and 3, it's the same answer, correct? And so what we do is we can take this vector u, and I'll just slide it over here. Oh, evidently v is coming with it, so that's bad. I didn't really want them to be attached, so I'll trace them in different colors. That helps me. Oh, and I'll do a better job. So here's v, and here is u. So just to kind of let you know, when we add two vectors, here's u, I'll just slide it away, because remember, a vector, it really could be anywhere. It's telling you a magnitude, which is the length of it, and a direction, which is an angle. And so if I add them, and I have u plus v, I add v to the end of u, so the end of the first one and then the beginning of the second one, and you can see that over there. Or if I start with v and then I add u onto that, it would look like this. But the resultant vector is that dark vector, and so I'll kind of move them back into their spot. So v plus u would be like this, and if I try to trace or draw that, this would be the resultant vector. And then if I have u in its original spot, and then I add v to that, the resultant vector is from here to here. And you should notice that if I slide those, out into the middle here, that they should be the same vector, correct? And so this gives us a parallelogram when we put kind of both of those together. Let me just slide that over there. And so we can either have u and then v, or v and then u when we add them together. And do you notice we get an oblique triangle, non-right triangle? It could be right, but it doesn't have to be. And so this is kind of our definition of vector addition, and we add one to the end of the other. And okay, then I'm going to put this back up because for some reason I feel like I had it there. And this is called the parallelogram log. So make sure, if you hadn't written it last week, whenever that was, when we're adding two vectors, the resultant vector is the diagonal of a parallelogram having adjacent sides u and v. And subtraction, that's just this next little thing. Subtraction is defined as adding the opposite. Just give me a head nod. Do you remember what an opposite vector looks like? Yes or no? So an opposite vector, if this is vector v, so to speak, then negative v just goes in the opposite direction, but is the same magnitude. So, and a lot of times we start it down here. It's hard for me to write it exactly the same way. So if this is vector v, this would be the vector negative v, or the opposite of v. And so when we define addition like we do with numbers as adding the opposite, then that will be the same. If these are, do you remember what format this is called? Because you know we barely had any of this. Just give me a head nod. Do you remember what that format is called? What way of saying that? That's the vector in component form. So you will want to know those words as we go through. So if we have vector u is equal to u1 and u2. Oops. Then that is the component form of the vector. We use those kind of greater than and less than symbols to look at that. If they're both in component form, we just add the x values, which is the first numbers, and we add the second numbers to get the sum. Scalar multiplication is k would be like a numerical value, and so we just multiply that so it either gets larger out or not. And then I think that's everything for that part. So make sure you have that written down if you needed to back that up and pause it. And then this just kind of reminds you of these negatives and the difference. So I'll just show you this slide. The negative, if the vector v is v1, v2 in component form, then the negative of v, or the opposite of v, is -1 times that vector. So negative v1 comma negative v2. And then the difference is u minus v is the same as u plus negative v, and we can get that kind of in component form, just adding those components. So we're super excited when it's in component form because we just add and subtract. If it's not, sometimes we have to use things like law of cosines and law of sines and things like that. So just be aware of that as we go. Then geometrically, using line segments, the terminal side is where the kind of arrow is, just a little reminder of that. And then here's a problem for us to try as we look at that. And so vector operation in component form is pretty straightforward. We will graph these as well, so if you want to find a piece of graph paper, that's awesome. When you write this, you want to call this vector v, and we can't write it in bold, so we do put that little arrow, like a half arrow, I'll call it, on the top, and it has components -2, 5, and w has components 3, 4. And so we'll do this numerically. We'll also do it graphically. So letter A is 2v, and again, we'll put the little arrows on it. So it's just going to be 2 times -2, 5. Oh, sorry, I was going to do a bracket instead of the symbol there. And so that one will be -4, 10 as we look at that. The next one, letter B, is vector W minus vector V. And so that's just going to be this 3, 4 components minus the -2, 5 components. And so the x value is 3 minus -2, or 3 plus 2, and 4 minus 5. And so 3 plus 2 is 5, and 4 minus 5 is -1. So we get 5, -1. Then take a minute and find v plus 2w. And what'd you get? Or 13 when you do that one. So -2, 5. When I double the other one, or I can just do that like and figure those out. -2 plus 2 times 3, and 5 plus 2 times 4. Or I could have, at first I was going to do that multiplying by 2, and then 4 here and 13 there. So I do want to go over just kind of the graphical representation of this, because do you remember when we did, like, navigation is the word that's coming to my mind, like the airplane or the boat or whatever, and it went this way and that way and all that kind of stuff. And so then when we do vectors, we're going to have a lot of that similar kind of thing. So it's a good idea for us to kind of have an idea of what those are going to look like. Let me find some graph paper here. And I think I can maybe kind of put them all on there. And I maybe can't see mine as I look at it. But just to remind you, when we have the component form of the vector, if you're going to draw that vector, where does the vector start? At the origin, right? So the vector starts at the origin. Vector v was negative 2, 5. So negative 2 and 1, 2, 3, 4, 5 is right there. And so this is vector v. And I'll kind of color code them. And so then we put the arrow on it, because it's component form, it's starting there and kind of going. And then since letter A was 2V, then we just double that. So there's a second one of these. I'll just clone it, and that makes it a little more consistent for me. And so when I put that one up here, oops, then it should also be at this point. And what is that point right there? So it's negative 4, 10, and that's what we got as that answer. Oops, that's the coordinates of that point. If we're just thinking of the, or negative 4, 10. Wow. Of what the coordinates are of that point after we put those two vectors. So that's what letter A looks like. For letter B, we did W minus V. W is at 3, 4, 1, 2, 3, 1, 2, 3, 4. So that vector looks like this. And so when I do negative V, I can go from this end point at W, this end point right here, and then I'm going to go kind of the opposite of V. And so if I think of distributing that through, instead of V, which is negative 2, 5, I would get the opposite of that, which would be positive 2 and negative 5. So when I kind of figure that out, I can go positive 2 and then 1, 2, 3, 4, 5, and I end up right there. And that point should be where I ended up as we look at it. And then for the first one, it's hard to tell what the maybe resultant vector would be, but for this one, it's a little easier, and I'll maybe draw it in a little different color, like a pink color. So the resultant vector is that vector that goes right there. And I'll put the arrow in pink. There we go. As we look at that. And then the last one, we'll just kind of look at that too. Just kind of going through these pictures kind of will help you down the road when you have to do more manipulating of things. So this one is V, and we already had a V there, which is negative 2, 5. So I'm going to use this green color, but I'll just trace over that. So here's that negative 2, 5. And then I need two W's. W is 3, 4. And I'm going to do that as kind of adding the one onto the other. So I'm going to start at this endpoint. And 1, 2, 3, 1, 2, 3, 4. There's one W. If I added one W there, it would go to right there. And then, oops, let me Let me get rid of that. And then if I just clone that, and since it's 2W, I can get that second one up there. It does go off of my graph, but it gives me the idea of what's happening. And then my resultant vector for that one, and I'll draw it in like a lighter green color, goes from the beginning of the beginning to the end of the end. And we know that that point is, what is it? 413. So 1, 2, 3, 4, and then up to 13. So we can kind of see where that is. Just to give ourselves a visual so that when it comes to the point when we have to kind of do all that trigonometry, which will be in our future, then we know kind of what that's going to look like. Oops. So then I also have the pictures here, and the reason I went through them there with you is I'm going to get rid of that, oops, on the SmartNote file. So this is properties of vector addition and scalar multiplication. And I'm just going to leave that up there a few minutes in real time and let you write down whatever you think you need to for that. I will just read through it briefly as you're maybe writing. So properties of vector addition and scalar multiplication. So let u, v, and w be vectors, and little c and d, which are in regular print, are scalars. Then the following properties are true. That u plus v equals v plus u. That's the commutative property of addition. U plus v, number 2 is u plus v in parentheses plus w is equal to u plus parentheses v plus w. That's the associative property of addition. 3 is u plus 0 equals u. That's the identity for addition, is that 0. And do we agree that that's a bold 0, so it is not the number 0, but it is the vector 0, 0 in like the little parentheses, or greater than or less than. U plus negative u is 0. That's the inverse of addition. So those are all properties we've had a long time ago. Then 5, if you take that scalar multiplication and you multiply c times d times u, or c times d and then times u, you'll get the same answer. And so that's the associative property again. Then the distributive property is in number 6. Notice for the distributive property, it's scalar plus scalar times the vector, and you can do that. If c and d were vectors, no, this is no longer going to be the case. So c, unless you had the scalar, if they're all 3 vectors, you can't do it like this. So in number 6, c plus d, which are the scalars, times vector u is equal to cu plus du. And then same thing here, c, the scalar, times u plus v is equal to cu plus cv. Multiplicative identity is 1, and the multiplicative inverse is 0. And 1 and 0 are scalars, correct? Just scalars. What do the double bars mean? Do you remember? That was last week. The magnitude. The double bars mean the magnitude, and so that's the length or distance formula or Pythagorean theorem, kind of whatever version you need at the moment. So if I'm multiplying by a scalar, I can either multiply the vector by the scalar, then find the magnitude, or I can find the magnitude and multiply by the absolute value of the scalar. And do you know why that's an absolute value? Think about that, because think about this, even if I multiply, like, suppose the vector is 3, 4, and I multiply by -1, I'll get -3, -4, right? But when I find that distance using the Pythagorean theorem, they'll both be positive, right? And so that's why if I don't do that first, it'll still be multiplying by the absolute value of that, or the positive of that. So the next thing is unit vectors. So the big thing with a unit vector is its length is 1. And so think about this. If we know the magnitude and direction of a vector, if we know the magnitude, that's the length, right? If we just take it and divide it by its length, what will its length now be? 1. Do you agree? If you take its length and divide by its length, you're going to get 1 no matter what. And so that's really the big thought in this idea of unit vectors. So in many applications, we really want the unit vector because the unit vector has because we want that direction. So then a unit vector really just gives us the direction. Do you agree? Because its length is 1, and we can multiply it by anything as we want to. And so in many applications, we want to find a unit vector. So the unit vector is a vector of length 1. So you need to know this, that because I guarantee you will be asked to find unit vectors. If this vector u is equal to a unit vector, if and only if vector, if and only if it is some vector v divided by its magnitude. And so then, you know, they also write it this other way. You can think of that as 1 over the magnitude times the vector. And note that u is a scalar multiple of v. So if we want to compare this u and this v by themselves, then we just are multiplying by this 1 over the magnitude, which is just a 1 over the magnitude, which is just a numerical value or a scalar. So I'll maybe write that 1 over the magnitude of v times v. So that is the concept of a unit vector. Now, think about the fact of how you get that magnitude. You're using either the Pythagorean theorem or the distance formula, correct? Which, you know, are just variations of each other. And so you will get things in simple radical form, right? Does that make sense? And so that magnitude could be a radical thing, and you're going to have to kind of figure out what to do with that as you multiply it. And so then our next job is to find a unit vector and then verify that it's a unit vector. So find a unit vector in the direction of v, and, you know, I'll write number 4, v. And I like to just rewrite these because we don't have a way to write bold. So it's the vector v is -2, 5. And then verify that the result has a magnitude of 1. And so our first job is just to take, there's the vector. What do we need to figure out? The magnitude. So we just need the magnitude of v, which, how are we going to find the magnitude of v? Somebody just tell me. What am I going to do? Okay, yep. So tell me specifically. Okay, square root of, I'm going to put -2 in parentheses, squared plus 5 squared. And so that is square root of 4 plus 25 square root of 29. Just give me a little, yeah. So that is the square root of 29. And that's our first job. And then v is just this vector. So I'm going to call u the unit vector of v, and that's going to be vector v divided by the magnitude of vector v, or, you know, 1 over times vector v. And so in this case, it's going to be -2, 5 over the square root of 29. And so really I can say that is -2 over the square root of 29 and 5 over the square root of 29. May I leave it like that, do you think? No, I have to get that in simple radical form. And so just a reminder, I'm going to multiply by the square root of 29 over the square root of 29. Luckily, in a way, nothing, that doesn't even turn out to be anything in simple radical form. So this unit vector is 2 the square root of 29 over 29, thank you, negative, and comma 5 the square root of 29 over 29. And in my mind, it doesn't need to be said, but I better say it because these are exact values, correct? And so we're giving exact values, things in simple radical form, and that's kind of what's happening here. So that was to find the unit vector. So I wrote most of that in black. I'll do that. Then it also says to verify that its magnitude is 1. How am I going to verify that its magnitude is 1? Here is the unit vector. How am I going to verify that its magnitude is 1? I'm going to find its magnitude. Does that make sense? So in order to verify that its magnitude is 1, I'm going to find its magnitude. And so this is kind of the second part of the problem. And really, if you can verify one unit vector has the magnitude of 1, they all turn out to be kind of like this. But it is actually going through, and it should tell you if you've made a mistake, generally. Like, I almost forgot to write the negative. Will I identify that when I find this magnitude? No. So some mistakes won't be identifiable. But to verify that, I'm going to show that the magnitude of u is equal to 1. So it's the big square root of negative 2 square root of 29 over 29 squared plus 5 the square root of 29 over 29 squared. Now, I could use a little calculator help. So, negative 2 squared is 4, square root of 29 squared is 29. So that's going to be 4 times, 29. Let me get rid of that. That's going to be 4 times 29 over, I don't know what 29 squared is, 841. 841 plus 5 squared is 25 times 29 over 841. And, since it's verify, I'm really intending to show that as I go. And then more help could be, what's 4 times 29? 116 over 841 plus 25 times 29. 725 over 841, and then when I add those, 6 and 5 is 11, 3, 4, and 8. So I get the square root of 841 over 841, which is the square root of, well, which is 1. I'm not even going to write another version of that. So the magnitude of u is equal to 1, and that checks out for us. So just a verifying problem. I would say as you go through things, just being careful about checking to make sure that it is a unit vector as you go through. So one thing I'm just going to go back up here and say again is, do you remember what form that's called? Component form. And I'm actually going to write it here. I have it over there. This is called component form of a vector. And the reason I'm saying that again is because when I give this test, there's different forms. This is component form. It's easy right now because we're using it right now, but sometimes I'll ask you to use different forms, and so the component form is the one with the little greater than and less than signs, because our next form is going to be called the linear combination of form. And well, I'll wait until, oh, there it is. So Now, there's two unit vectors. Do you agree that the magnitude of these two vectors that are on the screen right now, this one and this one, the magnitude is 1, right? Square root of 1 squared plus 0 squared, square root of 0 squared plus 1 squared. These are standard unit vectors. And think about what those points are. And they are called vector I and vector j. Maybe right away you're noticing a little issue here. See that letter I? Does it stand for the square root of -1 right now? It does not, okay? So that is a little problem, but right now that people sometimes have an issue with. The book authors, if it's a bold I and, well, I'll show there, yeah, usually the I that's the square root of -1 has that little hook on the bottom. It's a, italicized, yeah. It's an italicized I, which is the square root of -1. When it's the vector I, the unit vector I, then it's bold in a book typeface, and then when we write it by hand, we put the little arrow over it, and so we'll know. So think about what that is. They give us the direction of the positive x-axis and the positive y-axis. So if I plotted this point 1, 0, or I went out 1 and then 0 for this I vector, then I'm going to end up right here. So that gives me the positive x-axis. If I use this j vector, it's going to give me this vector that's right here, and I stop at this point 0, 1, and that's going to give me the positive y-axis. And then what we can do is we can put some scalars on there, and then we can multiply I times, we'll say 4 for a minute, right? So if I multiplied I times 4, it would be out there, right? And go out to 4. And I can multiply j times 3 or something like that. And what I can do is then I can get vectors that are all out in any of those quadrants by using those two vectors. And, oh, okay. And I think I have some slides out of order. And I just did not realize that necessarily. And, oh, maybe these vectors can represent. Oh no, this is it. Yeah, on my notes I have some things kind of messed up a little bit. So these vectors can be used to represent any vector v as follows. So just some things to know. This vector v, maybe write that down. What form is that in? Component form. So there's our component form of that vector. And so then if we want to represent it in this kind of new form, that using these linear vector unit vectors, we can take 2 times that I vector plus -3 times that v vector or j vector. And what we get is -2i minus 3j. So this is the same vector. This is called the linear combination form. Linear combination form. And it uses those standard unit vectors, I and j. So I is right there and j is right there. And then these scalars now, so now 2 and -3 are considered scalars. They are called the horizontal and vertical components of the vector v that we're looking at. So this is a big concept. As we get to the testing part of this chapter, we're just at section 3. But as we get to the testing part of this chapter, knowing if you're giving you're asked to give an example or an answer in component form or linear combination form. Hopefully you agree neither of them is super hard, but it's just, you know, making sure you're doing the right one as we look at it. So the next one I'm going to graph as well, and I think I have it set up on graph paper. We'll see as we go. Oh, so here is the words. I should put that up too. So the vector sum v1, so v1i, which is with the arrow, plus v2j, which is the linear combination of those vectors. And any vector can be written as a linear combination of standard unit vectors I and j. So now we're going to get a vector. We're going to get an initial point, a terminal point, and our job is to give it as a linear combination, okay? And so I'll graph it on here as well. And so here it is. I have my graph paper all ready. So this is number 5, and it says let U be a vector. So U is a vector with initial point at 2, -5. So by the way, the other thing to be careful in this chapter is it coordinates of a point, which that is, or is it the component form of a vector, right? So lots of little just things to notice. And a terminal point of -1, 3, and then we need to write U as a linear combination of standard vectors I and j. So the first thing I would do is just like, you know, plot that out. And so 1, 2, -5. I don't know if I can quite get down to there. Maybe I'm going to put my graph paper up a little higher so it's easier for me. But I'm at 2, or is it +2 or -2? All of a sudden, yeah, all of a sudden my 2 there looked like a negative to me. 1, 2, -5. 1, 2, 3, 4, 5. So this is the initial point, and -1, 1, 2, 3 is the terminal point. So it goes from the initial to the terminal. So I'm going to put an arrow on there as well. And let me just kind of find some things here. And I think this was the initial. This is the terminal side. And so I'll put my arrow there as I look at that. And then what is the I part of that, do you think? How am I getting, think in terms of this, how am I getting in terms of x value from here to there? What is the x change or move? -3, I think, right? 1, 2, 3, right? And what is the y change? It looks like 8, right? And it's +8 because it's going up 8, right? Versus -8, which would be going down 8. And so one thing I want to think about is I would actually get this in component form and think about, you know, it's the change in x and the change in y, correct? And just like with slope, we do the terminals or the second point minus the first point. Does that make sense? As we go do that. So the first thing I'm going to do is I'm going to put U in component form, and I'm going to say to get U, I'm going to take, if I call these kind of x1 and y1 and x2 and y2, I'm going to take x2 minus x1. Those have to be x2 terminal, and y2 minus y1. Ooh. And so then -1 minus 2, comma, 3 minus -5. And so then I get that -3 and +8. So this is the component form of U. And but I'm asked for the linear combination answer. So my answer as a linear combination is just negative 3i plus 8j. And by the way, did you notice how I wrote that I and j right now? I tend not to put a little dot above the I or j. I just change it into an arrow. So the answer for this one is negative 3i plus 8j. Okay, so take a moment, and here's the next one. Find 2u minus 3v. So just take a moment and do that. And I'll ask you what you get. And in my mind, it's an algebra little problem. So, the way that, now I'll go over this one. So we want 2u minus 3v, and it didn't say anything, so I would leave it in the form that it's in, this linear combination. And so I'm just going to take 2 times u, which is negative 3i plus 8j, and minus 3 times v, which is 2i minus j. Oops, and I forgot my arrows on these first ones. And so I'll have negative 6i plus 16j minus 6i and plus 3j. And then I get negative 12i plus 19j. So just to kind of think about that. Now, really, I want to go through direction angles. We'll really do that part tomorrow, but I want to do the introductory slide of it just so that we kind of, our brains can mull that over. So this is direction angles, and when we think about a unit vector, so if we have a unit vector, what's its length? 1. And think about that unit vector can be in any direction. And so if we put together, you know, a lot of those directions, do you agree that the endpoints of those would be a unit circle, right? And so we're back to the unit circle, back to the table of trig values that we know, and so a lot of this is going to be related to the trigonometry that we've done before. So if u is a unit vector, and such that theta is the angle measured counterclockwise from the positive x-axis. Do you agree that's the angles we've been using all along? Our angle is, theta is the angle measured counterclockwise from the positive x to vector u. Then, do you remember that this point is cosine theta sine theta? Do you remember that? And so when we do that, u in component form is cosine theta sine theta. That's in component form. And what form is it here? linear combination. So linear combination form, it's right there. And the angle theta is the direction angle of vector u. So do you see that we're going back to the whole trigonometry and that unit circle that we've done before? So we'll talk about that more tomorrow.